The next few videos, starting with this one, we're going to take a closer look at the wave equation. Now there's different forms of the wave equation. Here we're going to look at the wave equation of what we call a wave train. Let's say that we have a string, and on one end we're just continuously moving the string up and down so that we're continually pouring energy into the string. That energy will then displace itself along the string, causing a wave to move to the right with velocity v. Now notice that the string particles will move up and down. The string particles do not move to the right. It's just the energy of the wave that moves to the right. It's just a string that moves up and down. So there's displacement in the y direction and then the velocity in the x direction. Notice that this is then defined by the wavelength, and that the greatest distance from the central equilibrium point of the string to the highest displacement is called the amplitude of the wave. Now the displacement y, so the particles in the wave that are being displaced in the y direction, are a function of the position in the x direction and the time that has elapsed. For example, as this whole wave moves to the right, if I just stay, for example, at this point right here, notice or I'll go over here, it's a little better right there. So if I go to this point right there, at this location, notice that at this moment in time, at that location, my displacement is this large right here. But then as the wave moves to the right, a very small amount of time later, when this wave has now moved like this, you can see that now my displacement is a little bit smaller. A small amount of time later, when the wave continues to move to the right, my displacement changes. You can see from any point along on the x-axis, the displacement of the wave depends upon how much time has elapsed and how fast the wave moves to the right. If I then, on the other hand, take a snapshot saying, okay, this is what the wave has in this moment in time, and I don't let any time elapse, and I then go to different locations on the x-axis, for example, here or there or there. If I'm over here, my displacement is this much. If I'm over here, my displacement is in this much in the negative direction. Over here is this much in the negative direction. Over here is this much in the positive direction. So the displacement y does depend upon where you are in the x position and how much time has elapsed. So let's first start out, to make things a little bit simpler, let time equal 0. So, in other words, time is frozen. And let's say that time is frozen at this very moment in time when the wave is right here. Okay, so what does that wave look like? Well, that looks like a sine or a cosine function, and since at time equals 0, so let's say time equals 0, the amplitude is a maximum right here. Well, that looks like a cosine function. So we could say that y is equal to the amplitude a times the cosine of some function of x. Not some function of x, but some constant times x. So let's see where this is simply a constant. Now the question is, what is that constant equal to so that we can describe this wave? Well, notice if an entire wavelength has gone by, like this, and we're back over here at the very same positions before, if an entire wavelength has gone by, then at that particular value for x, I get the very same value as I had when x was equal to 0. So for what value of the cosine of cx, so the way to look at it is, so the cosine of 0x is equal to the cosine of cx, which is equal to 1. Because then I multiply 1 times a, and I get this maximum displacement, which I get again when I'm over here. So what is this position right here? X is equal to question mark, so that I get the very same value for the displacement as I get when x is equal to 0. So from that, we should be able to figure out what c is equal to. In this case, I want this value to be the same as 0. And remember that the angle is repetitive, so I get the cosine of 0 must equal the cosine of 2 pi, which must equal the cosine of 4 pi, which is equal to the cosine of 6 pi, and so forth. So that means that for every displacement of 2 pi, or I shouldn't say displacement, for every 2 pi, I'm back to the position where I get my maximum amplitude. So that means that Cx should equal 2 pi. So Cx equals 2 pi for the first location, which means that x is equal to 2 pi divided by c. What value should I get for c? How far do I have to travel in x direction? So what is this distance equal to? Well, I know this distance is equal to lambda, the wavelength. So if I plug in wavelength for x, so that means I'm going to plug in a wavelength for x. So I have wavelength is equal to 2 pi divided by c. And if I solve that equation for c now, I get c is equal to 2 pi divided by the wavelength. Bingo, that's what I was looking for. I wanted to find the value for c here so that this equation represents this wave function right there. So let me plug that in and see what we get. So we have y is equal to a times the cosine of, instead of c, I'm now going to write 2 pi over lambda times x. Now notice, if x is 0, I get the cosine of 0, that's 1. 1 times a gives me a, which is correct right here. If I now plug in one wavelength for x, so I'll let x equal lambda, and I plug that in here. So let's try that. So I'm going to write y when x equals lambda, and of course t is equal to 0. I'm ignoring t for now. So this would be equal to a times the cosine of 2 pi over lambda. And of course, instead of x, I'm going to write lambda, like so. Notice that the lambdas cancel out, and I'm left with the cosine of 2 pi. And of course, the cosine of 2 pi, that's again 1, because the same 2 pi is the same as 0, and 1 times a is a. I get this value right here. What if I plug in 2 pi, or not 2 pi, but 2 lambda? Let's go to the next position right here, right there, where now I've traveled another lambda. So now my x is equal to 2 lambda. Okay, we have the value of y, which is displacement, when x equals 2 lambda, and of course t is still equal to 0. I'm simplifying things, so letting t equal 0. And I plug that in here, my equation. I get this is equal to a times the cosine of, my constant was 2 pi over lambda. And now instead of x, I write in 2 lambda right there. And notice that the lambda cancel out, and I'm left with the cosine of 4 pi. And of course, the cosine of 4 pi is again 1. And again, I have my maximum displacement. So it looks like I found my correct equation. I guess I should box this point right here. So that y, which is a function of x and t kept to 0, is equal to a times the cosine of 2 pi over lambda times x. So this is a very special constant right here. We call that constant the wave constant, and we give that value the value of k. So we introduce a new value, or a new constant, k, which is equal to 2 pi over lambda, which is now known as the wave constant, or the wave number. Which means that now if we're going to write an equation describing this wave motion like that, we write it as such. We say that y, the displacement in the vertical direction, which is a function of x, and a function of t, which in this case we're going to set equal to 0 to simplify things. It's going to be equal to the amplitude of the wave times the cosine of kx, where k is now understood to be 2 pi over lambda, known as the wave number. So that's the simple form of the equation, simply ignoring the fact that the wave is moving to the right, and so that this is constantly changing as a function of time. We will look at that in the next video to expand our equation. So in this case, we said the time is frozen. That means t is equal to 0, so we ignore that part of the equation. So we're going to look at it in terms of the position x. And so the displacement can now be described simply as a cosine or a sine function. Now you say, well, if you said this is a cosine function, how can you write this as a sine function? Well, I can have it start at a different location. For example, I can have the wave look like this. Notice it has this very same wavelength. The wavelength now goes from there to there. It's the same wavelength, but it has a different starting point. At t equals 0, the value of the displacement is 0. So that can be described by simply changing the cosine into a sine function. So I can say y as a function of x, and t equal to 0 is equal to a times the sine of kx. And notice it's the very same equation, just has a different starting point, and it doesn't really matter if you write it as a times the cosine of kx or a times the sine of kx. It's really the same thing. And that's how you develop the wave equation. If you want to see the second part of the wave equation, then tune into the next video, and then we'll take care of the portion where time is no longer equal to 0 and see how that equation develops.